Last but not least, in our data screening series, here is assumptions. So this will cover a little bit about what assumptions are and how to screen for them. So assumptions are things that we assume, clearly, that affect the outcome of our test. So these are the rules that we expect to have in place for our test to be accurate. So the statistic that we get, F, T, Z, is what we think it is. So there are several assumptions for basic parametric tests. That's ANOVA, t-tests. We won't really use a whole lot of non-parametric tests in our course, but do know that there are other tests that don't require these things. So this is your basic linear modeling type of information. So parametric tests assume independence, additivity and linearity, normality something or another, that's from the field book joke, homogeneity, sporicity, and homoscedasticity. Sporicity is kind of a special circumstance of homogeneity. So let me walk through those. So independence. Independence is something you can check for, but it's really complicated. So I would just say that you need to know that this thing is true because of the way your research is designed. So the errors in the model shouldn't be correlated. And this is errors based on participants. You can have errors in columns or questions on a questionnaire or something that have correlated errors. It's not the best thing in the world, but this is the participants' data don't influence each other. So participant 1 is their own thing, and they're totally separate from participant 2. My regression professor explained this to me as, let's say you're trying to take weight. So you're measuring people on a scale. It's really muddy outside. And now the data is no longer independent because the first person left some mud on the scale, and then the second person left some mud on the scale. So I am heavier than I should be because of when I came into the experiment and this other mud-related problem. So independence is that the people are different. If the assumption is violated, pretty much like you got lots of problems, but your confidence intervals and your significance tests will be invalid. That's also from the field book. I just find it funny, so serious. But independence is an important thing to know that it's true for your data. Additivity and linearity. And so I'm kind of going to make a quick chart here as we go about these particular assumptions. So let me just create myself a new little word here. And so what I'm going to do is kind of create you a quick table, 1, 2, 3, where it's got the assumption, the good name, the assumption, the bad name, and then how would I check? So let's start. We've got additivity and then linearity. Okay. So what is additivity? So additivity is based on the linearity assumption, but it doesn't have to be. Additivity can actually be for nonlinear analyses as well, but we're going to talk about it with a linearity assumption. So if I have several predictors, so this is generally a multiple regression problem, I want each predictor to add something to the equation. So that's the name. We want things to be additive. But if the columns are not additive, you'll get a specific error. So it's really actually a multicollinearity problem with 2 L's and not 3. So multicollinearity or singularity is the idea that the columns or the variables are too correlated to be used together. So they don't both add something to the model. And this happens when maybe you have some subtotal scores and then you also throw in the total score. Well, the subtotal scores add up to the total score, so they are not separate things anymore because now they are related. So if I can create the total score with these other columns, you'll get a singular matrix error or a non-invertible matrix error or a non-definite matrix error. It just kind of depends on the day. Those are 3 different errors that you can get that all point to this problem. So multicollinearity is the bad name for it. And or singularity. So additivity is the real problem is if you have multicollinearity. So what we're going to do to check it is run a correlation table. And this is really, if you have one variable, this isn't necessary. But if you have multiple variables, it is. So if you don't have multiple variables, just skip this step. Okay? So this is a regression, multivariate statistics, repeated measures sort of problem. Repeated measures does have a different rule. Most people tend to use 999. And this is basically just a quick check that the math isn't going to explode when you try to run a least squares analysis. So multicollinearity is when r is greater than 0.9. Singularity is when r is greater than 0.95. Sometimes you'll see this described as tolerance. Tolerance is 1 minus r. So the rules are reversed. It would be 0.10 and 0.05. So let's add those in. So we're going to use a correlation table. So that's the core function. Or I'm going to show you the symbols for numbers function. Sorry. So let's talk about how to check that. So we're going to run a bivariate correlation table. We're going to see if the scores are too high. If the scores are too high, so if your problem exists, pick one of the columns or combine them in some way, because otherwise you're going to lose power. If you're using the same variable twice, it reduces power and interpretation. And generally, this also causes suppression. So in a multiple regression sense, suppression is when you have two variables that are highly correlated with each other and with the variable you're trying to predict, the dependent variable. And so it's like having two measures of the same thing. So depression, CESD, and the back depression inventory. Those are highly correlated because they're the same thing. And they both predict PTSD symptoms. And so they sort of cancel each other out. And so the joke I used in my class was this is like having two very loud friends in the same room. And so they're just talking over each other and they just both get louder and louder until you don't understand what either one of them is saying. That is the idea of having a non-additive. So you want people to add something to the conversation, not cancel each other out. So the core function checks correlations. You do have to drop the factor columns. So we're going to drop those out and just check for correlations. So now we're moving on to assumptions. And if you need to know how I got to this data set, you're going to have to watch the other videos. But we're going to use the no out data set. Oops, sorry. We're going to use core, so no out. I'm going to drop my two factor columns. And I already know they're 1 and 2 because I've been working with this data set for a while. And then I'm going to use the use function equals pairwise dot complete dot obs, which is the same one you use for Homog+s distance. There's a giant correlation table. Look at this crazy table. There's so many numbers to check. Bah! So let me show you a cheat. So let's run that same code again, but save it this time as correlations. Okay. So I've saved my table. Here's one thing you can do. You can click on it and you can sort it one column at a time. So that is one way to do it, but if you have 900 columns, that's not going to work for you so well. So what's another solution? It's this cool function called symbols for numbers. So sim for symbols, num for numbers here, and I'm going to run that on my correlation table. And so I'm going to run that, and look what I get. I get this nice, neat, adorable little table with some symbols in it. So what is it? Well, here's the legend down here, appropriately labeled legend. So what it does is it says from 0 to 3, it's just a blank space. So all the little blank spaces like here means that that correlation is somewhere between 0 and 0.3. The little dot here, so like this dot here, is between 0.3 and 0.6. My commas here between 0.6 and 0.8. A plus would be between 0.8 and 0.9. A star would be starting at multicollinearity, so 0.9 to 0.95, and a B would be the range for singularity. And so you just want to check real quick below the ones. So the 1 is it correlated with itself, which will always be 1. And so I want to check for stars and for B's. If I don't have a star or a B, I'm good and I can move on. If I have a star or a B, I have to figure out where it is and then decide what to do. Okay, so we're looking for a star or a B to indicate multicollinearity or singularity, which is a problem with additivity. So that's how you check for bad correlations. Okay, next one down, linearity. So linearity is the parametric assumption, is that their relationship between variables is linear and not curvilinear or power function or quadratic. And so most graduate statistics, like Graduate Statistics 1 courses, should be called linear modeling, because that's what most of the things you do are: t-tests, ANOVAs, regression, factor analysis. So all that is linear. Non-parametrics is when you get into non-linear modeling, and it's really all least squares. So we're going to always test for linearity in this course. And so you can check for univariate linearity by creating bivariate scatter plots. So 2 by 2, no extra variables. So 1x, 1y. And make sure you don't see any curved lines or rainbow shapes or curvilinear patterns. So you can do that in ggplot2, or you can use that with the plot function. If you have 14 variables, that's going to take you forever, because 1 to 2, 1 to 3, 1 to 4, oh my god, I can already tell this is going to be too much trouble. That's the univariate function. Instead, we could do it in a multivariate way and look at all of the linear combinations. Okay, and that's especially important for multiple regression and MANOVA and repeated measures. But you could say that MANOVA is just a special case of repeated measures, but I digress. What we want to do is make sure that all the pairwise combinations are linear. So we're going to use this multivariate analysis. This is much easier. It allows us to check everything at once. If that analysis is really bad, and I should probably put that in bold, because your really bad and my really bad might be different, I would then go back and check and see which variable it is, or I would just maybe use the RFIT package or one of the other non-linear, non-parametric estimation methods. So we talked about this a little bit in the last video, but what I'm going to do right now is create myself a fake analysis. And I'm creating myself a fake analysis because I'm not running a real one. I'm doing data screening before the real analysis, and I'm going to run a fake regression so I can get these diagnostic plots. And this type of data screening procedure can work on any analysis that you want to check assumptions for. Accuracy, missing outliers, parametric assumptions. And so I don't have to remember all the little rules for each individual function. I could do this one big analysis. So it would be a fake regression because this is not a real hypothesis test. This is fake. If you want to run real multivariate, if you want to run real regression, just run the regression for real. And so at this point, it's both the analysis and the data screening at the same time. But right now we're going to do this as fake because I haven't told you what I'm going to do with this data. So we aren't doing a real hypothesis test, hence the name fake. Lots of these R functions have diagnostic plots built into them, but this guide allows me to apply data screening to any type of analysis, specifically parametric analyses. Okay? All right, but there are still things that you were going to do for ANOVA that apply to ANOVA, and you would only do them then, like Levene's test. So we're going to create a random variable to start. And why am I doing this? Well, if I want to screen my entire data set, I need something else to screen it with. And so we're going to use chi-square. And so why chi-square? And Multicollinearity, remember, was chi-square, so what gives? The idea is that for these assumptions, the errors in a model. Now, errors are the difference between your predicted score and your actual score. So error is really like how close am I getting to predicting your real score. Okay, so if I use the mean as my model, standard deviation is how close I got to estimating people's actual scores. Okay. And the errors in a analysis are going to be chi-square distributed because there will be lots of small errors and only a few big ones. And this is treating error as a positive number only. Generally errors are squared, hence the name least squares. But if you think about the distance function of Multicollinearity and that sort of idea, how far away am I from predicting your score, those are chi-square distributed. Lots of small numbers, only a few big ones. Okay. If I take those numbers and standardize them, meaning I z-score them, now they're going to be normally distributed around 0. So don't get these two things confused. The errors should be chi-square distributed, so I'm going to create a chi-square fake random number to compare them to. if I standardize them, they're now normal. So we're going to use both of these things at once. Okay. The z-score things are normal because they're z'd. The actual errors are chi-squared distributed. Okay. And we're going to make these pictures, so I'm not going to draw it just yet. So that's why chi-square. Why random? Well, I need a variable, so I'm just going to make up a random one. The other thing is that the errors should be random in a data set, in the sense of if I'm predicting a random variable, the errors should be random, which means that the pictures we get should look like a bunch of messy dots. And so we're creating a random variable with a chi-square distribution for a reason. And if you don't totally get why, that's okay. But when you get into like doing the math for this, it starts to make a little more sense. So the errors should be chi-square distributed. The standardized errors are going to be standardized distributed, so a normal distribution, and we're going to use chi-square for that reason. So let's create a random chi-square variable. The good thing about R is that it actually does do random numbers. So if you're used to doing this in SPSS, everyone would get the same random number, as long as you all did the same procedure, which is not really random. So your pictures, if you're doing this along with me on your data set or my data set, might be different than mine because this is truly random. You can set the C so we all get the same random number, but that's not nearly as much fun. So that's important for repeating analyses, but right now I'm just going to show you, we might have different pictures, but that'll help you with interpretation looking at a lot of different pictures. Okay. So we're going to use the r chi-square function instead of q chi-square from Holomos. So the way r chi-square works is that you have to tell it the number of things that you want to estimate, so number of rows for my no-out data set, and then the degrees of freedom. There's no real reason 7 here. I'm just jokingly calling it the magic number. 7 seems to work. So I've been doing this analysis this way for a while now, and 7 just seems to be a number that seems to work. It's like magic. I don't totally know. Don't use a number that's too small, like 3 or less, because you don't get quite enough variance for your data set. You could use the number of columns, but it doesn't matter. So 7 seems to work. So that is just because I like the number 7. If you're in the real world, my favorite number is 5, but you know, potatoes. So the assumption here is that it's not curvilinear, and we are going to do a fake regression to check this out. And we haven't gotten to how I actually check this yet. So let me start by making my fake regression. And for that, I need a DV. So we're going to make our random variable. So r chi-square. There we go. So n, so number of rows in my no-out data set, so I can use this code no matter how big the data set is, and then the magic number 7. So that makes me a random number that's the same size as the data set. That would be different every single time. So if you look over here, 842318, run it again. Oops, sorry. If I can remember to hit the right command here. Okay, there we go. And now I have slightly different random numbers. So we will get slightly different pictures here. Okay, so now that I have this random data set, what do? We're going to run a fake regression with that as the DV. So we're going to use the LM function, linear model, for regression. Don't create a random variable and then don't use it. That's just silly. Okay. So the way that LM works is that you do y is approximately x. So we're going to use the little tilde here because we don't want to set y equal to x. That means we're setting the variable to literally x. What we want to do instead is estimate. So tilde means estimate. So predict y with approximately x. And that's a little different than most people think about it. Generally, we're talking about x predicts y. Well, written code-wise, it is y is predicted by x. Okay. Comma, data equals the dataset name. Lots of options here, but these are the only ones we're going to use right now. So y, we're going to fill in with the column name for our DV, which is random right now. And x, we're going to fill in with the column name for our IV or IVs. So if you're only going to use 4 of the variables, just type those variable names. This plus this plus this plus this. Okay. But we're going to cheat and use the entire data set because we want to screen the entire data set for problems. So a dot represents all the columns. So that's kind of a quick and dirty way to do it. So random is approximately everything. Data equals data. If you have specific columns, you would have to type them out. Column 1 plus column 2 plus column 3 plus column 4, filling in the column names. So let us try that. So we're going to call it fake because it is a fake regression. Let me use LM. So my DV is random, is approximately dot for all the columns, comma, data equals no out. That saves over here as a list, and it is a huge list of a bunch of stuff. But I wanted to save it, because now I'm going to only use parts of it. If you don't save it, it isn't there for you to use again here in a minute. So we're saving it. Okay, so I can view these plots. So long story coming around back to how do I check for linearity? We're going to make a linearity plot. Sometimes it's called a normal probability plot or a PP plot. Sometimes it's called a quantile plot or QQ plot. So in SPSS it's actually a PP plot, but in R we're going to make it as a QQ plot. Same difference. Okay. And so it takes a while to get used to looking at these. And I jokingly call this the Sarah Squint test because I had a GA a while back that told people basically squint at it. If it looks like a line, it's a line, and move on. So you don't have to be super picky here. This one on this side is starting to be nonlinear because of that bow shape that it's making. I actually probably wouldn't blink at that one too much if I had a lot of data. This is like perfect. This never happens. So let's look at one of ours and see what it looks like. Okay. You will always have one random dot that just gets on your nerves, just as an aside. So what is this thing plotting? This is plotting the standardized residuals. Okay. So let me kind of try to chicken scratch this on here. It's not going to be pretty. I'm warning you in advance, but I'll try. What we've done is we've created X and Y, okay, where Y is the predicted score and X is all of our variables. So we've got a random score here in Y and all of our variables on X. If I'm using all of my data to predict a random score, I'm going to get it about 0% right. So I'm going to have probably a flat regression line because it's random and I'm just picking things. Okay. So given that, what we can do is calculate the residual scores. So we can calculate how far people are from the line away from a random prediction. And so if we're predicting them randomly, their scores from this random prediction should be random and chi-square distributed. So what we're going to do is tell it to pull out all these residuals. So how far away am I from predicting the person? And given these residuals, standardize those. And then standardizing them just makes it easier for us to read the graphs, really, because then they're standardized. So the z-score values of how far away I am from their actual score. And we're going to use z-scores because it's easier and gives us probabilities. And so let's get those standardized residuals out of my fake regression. And so that function is called rStudent. And literally I'm going to type exactly that. So let's get those standardized residuals. rStudent of my fake regression. Okay. So now I have a whole list of all their standardized residuals. So I could real quick plot those. Okay. It'll give me a bunch of dots. I actually probably more so wanted to do a histogram, but I don't want to preview something that I'm about to go through. So we'll just hold on to. We're going to plot those using the QQ norm function. So QQ norm of standardized. Okay. And I know that LM has diagnostic plotting, so you could just type plot fake, but I have a little more control if I plot them this way than if I use the automatic diagnostic plots. So I know it has the plot functions, but I'm going to show you like very specifically this is how I get just this plot so you're not confused. Okay. So here's my QQ norm plot. So let's make that a little bigger. So okay, it looks moderately linear, but there's no line, so I'm confused. So what we're going to do is type AB line 0, 1, and that will add a straight line to the graph for us. So AB line's function is y-intercept comma slope. So it's plotting a y equals x for us. So that makes it a little easier to see, and I would say this is mostly linear. The dots are pretty close to the line, right? You will always have that one annoying person way up here, way down here, but it's not very close. It is hard to predict people in the tails because there aren't that many people out there. So the less people you have, the harder it is to predict. So you want most of the data to be very close to the line here, so squint at it. If it looks like a line, move on. So what is being plotted? Well, here's the theoretical quantile. This is z down here. So this is the z normal distribution. This is your distribution of residual scores. So this is the plotted residual standardized scores versus a real z-score distribution. So you especially want the data around 0 to be linear because that's where most of the people are in your data set. So I would say that looks pretty linear. This is a QQ plot, sometimes also called a PP plot. All right, so that's how we checked for that. And you should get a slightly different picture than me because we have different random numbers. But in general, it will be pretty close. Okay, so we're checking that with the QQ plot and the squint test. So moving on, let's talk about normality. So the normality assumption gets interpreted that the data needs to be normally distributed, and that is such a lie. It's actually the sampling distribution that has to be normal. And so if you haven't ever watched the distribution bunnies video, you should Google central limit theorem bunnies and go watch that. And it talks all about why the sample doesn't need to be normal, the population doesn't need to be normal at all, it's the sampling distribution that needs to be normal. So if our sample is, it's okay, as long as we have enough people to meet the central limit theorem. The magic number is 30. If I have a small sample, I will have to use that as an approximation because it's the only thing I have. And so really the normality assumption matters most in small samples because at the central limit theorem, with at least 30 people, the parametric and non-parametric tests give you the same answer, so the normality assumption can be bent. As long as our sample is large enough, outliers are usually a bigger deal. Okay. I'm going to tell you how to check it either way. So with univariate normality, what I can do is check that the individual variables are normally distributed. And so you can do that with the histogram function. So it's hist, lattice package has histogram, but hist, H-I-S-T, is in base R. So you can use that one. But also skew and kurtosis. And so I always have students, so we're on normality, who will look at a graph. So let's make a histogram here of one of our columns. Let's go for, I think 13 is the problem child. And they'll look at this graph and they just don't know what to tell me. They can usually tell you it's skewed, but they can't tell you if it's bad or not, right? So give me a number, give me a reason. And so what we're going to do is calculate skew and kurtosis. So we can put actual numbers to those because we know what a normal distribution is supposed to look like. So we can tell how far it leans from normal, that's skew, and how much it is squished up or flattened out from normal, that's kurtosis. And so we're going to use the moments package because it will calculate skew and kurtosis pretty easy. And so what I'm going to do is remember to load moments. So you should install moments. If you don't have it, I have it. So I'm going to type moments. Okay. So the code is skewness. And then it's just dataset name. Okay. So it's dataset, NARM equals true to drop the NAs so that you can get the actual skew. Don't run this on a factor column or it'll be grumpy with you. So I'm going to drop my two factor columns. So negative C1 and 2 to drop my factors because my no out data, those two factors are first. It's much easier if you stick your factor columns at the beginning, just a word to the wise. NA.RM equals true to drop the NAs. And that will calculate the skew for each column. Okay. So what's a bad value? I'm looking at these numbers, they're all pretty close to 0. So a 0 skew means it's perfectly normal. Negative means it's negatively skewed, so ceiling effects. Positive means it's positively skewed, so floor effects. So this is a ceiling effect. It's negatively skewed because that's where the tail is. So skew is all about where's the tail. But most people consider a cutoff score of 3 to be too crazy. So this is like z-scores. So anything greater than or less than 3. So 3.5 and negative 3.5 would be bad. So I don't have any data that's too skewed, although it will look skewed, but it's not. The other one is kurtosis, so you just have to remember how to spell it, and it's the exact same code. So no out, and we want to drop our categorical columns, and then na.rm equals true. So drop those columns, and it's still the same rule, 3. So I have one column, rs12 here, that has a kurtosis of over 3. So I'm going to make another histogram of that column in particular. rs12. And look at that one. And really it's because everybody picks 7. So it's not actually skewed, but it is kurtotic or kurtotic, either way. And since it's too tall, it's a positive score, that is leptokurtic. Okay. Now, the solutions for skew and kurtosis often are transforms. I heavily advise against transforms because it actually makes it more complicated to interpret. It doesn't really change a whole lot. And then, you have to explain to people like the square root values are at mean is x, and it gives everybody a headache. So especially if your data set's larger than 30, I would tell you these are important numbers to look at just so you know what your data looks like, but on transforms because they're more trouble than they're worth. All right, so we went over this, yada, yada, yada. Okay, but it can be helpful for the next part. So for multivariate normality, all the linear combinations have to be normal. We've run our fake regression, we've run Mahalanobis, so let's check it with our fake regression. So we're going to take those standardized residuals and just plot them. So I'm going to use the histogram function. So back to this little chart here. So we're talking about normality, non-normal. So not a very good name. And we're going to use a histogram of the standardized residuals. All right. We can also use skew and kurtosis. Alrighty, so let's do that. So histogram, hist of standardized. Now I'm going to add the breaks function just to give myself some more bars to look at. So how can I tell if this is any good? Like I said, you always get this one annoying person out here. Now this is all graphed on the same data, so this annoying person will be in every graph. It'll magically disappear. Now what you want to look for is that the data should be centered over 0, so it should be mostly here over 0, and it mostly is. And usually it's between 2 and 2 or 3 and 3. So what you don't want to see is a lopsided distribution, where it's from 0 to 4, and where the data is spread out more evenly than this. So most of the data is here between 1 and -2, really. But you don't want to have like the chart to be cut off, so you don't even see the negative side. So it should be evenly centered around 0. As I say, this one's pretty good, and I have way more than 30 people, so I'm actually okay either way. So here's the other chart. So this is a different randomization of this data, so it's really much more normal, centered over 0 very well. So just talked about this. And let's move on to homogeneity. So homogeneity in several books gets lumped all together as one big assumption with homoscedasticity, and I would argue that you shouldn't. So homogeneity, this would be heterogeneity. What we're going to do to check that is a residual scatter plot. It also can be checked with Levine's test and Buchanan test. So that just depends on what you're doing. So what homogeneity is the variances of the variables is equal. If you have multiple groups, like you're running an ANOVA or MANOVA, then it's the variances between groups is equal. Okay. And that would be Levine's test for ANOVA and Buchanan test for MANOVA. However, the problem with those tests is they're heavily biased by sample size. So you really have to use this 001 rule so that they're not easily significant. So you don't want p less than 0.001 or 000, which is my new kids on the block rule. And so when we get to ANOVA, we'll talk about how do I run a Levine's test. So we're not going to do one of those now because I don't have groups to really run this on. Paired with homogeneity is this assumption of sporicity. Sporicity is specific to repeated measures type tests. And sporicity is sometimes called compound symmetry. It's the idea that the time measurements in repeated measures of the difference score between time measurements have the same variance, and that the correlation between time measurements are the same. And I use time to mean the repeated component. That doesn't actually have to be a time variable. So the variance, difference score, and the correlations between times are the same. Basically, the idea is that the variances are the same across time. Sporicity, personal opinion, is a stupid assumption. It has its mathematical reasons, because if you don't meet sporicity, it lowers power. But think about, sometimes we design research studies that specifically do not want to meet the assumption of sporicity. So here's an example. Let's say you're trying to get people to quit smoking. So you literally cannot have negative cigarettes. So the distribution is bottomed out at 0. And so you start with a group of people that range in a wide range. I smoke a couple, only when I drink, to I smoke 4 packs a day or something. Okay, I don't actually smoke at all, but you hear that a lot from people. I only smoke when I drink. And so you have a wide range of scores. And if your smoking cessation program is working correctly, those scores are going to come down. So people's scores are going to decrease over time. And it bottoms out at 0 since you can't have negative cigarettes. And so what's going to happen is the variance is slowly going to get smaller and smaller as the people at the top of the distribution come down. So this is the same example as weight. If you're trying to get people to lose weight, the people who need to lose the most weight will come down faster than the people who only need to lose a couple pounds. And so the variance will decrease over time. Sometimes that's called regression to the mean. But that's what you want. So you can't meet this assumption because of this test that the way you're studying this. It's also a difficult assumption to meet if you are testing people on the same thing over and over again because they get practice effects. So the variance might decrease because they're getting better at it, or it might increase because they're getting bored. So sporicity is a difficult assumption at best. But it's also kind of tied into homogeneity, the idea that variances are the same. But for repeated measures, it's called a different name. Homog+s test is the most popular test for that. When we get to repeated measures, we'll talk about that test some more. And so here's an example of homogeneity on this side, a non-homogeneity on this side, and this is really more sporicity. And so this, having wider variances, is bad. So that's heterogeneity. And so before I talk about how to check for homogeneity, I'm also going to talk about homoscedasticity, which is your Scrabble word for the day. Homoscedasticity. If you're one of those goofy people who spell with a K, whatever, we're cool. Right? We're also going to use a residual scatter plot. So you can tell what words I type a lot because these are in here as spell checked correctly. All right. So homoscedasticity is so often tied to homogeneity. They're not always the same thing. So I'm going to separate those out. They're both dealing with variance, but in a different way. So homoscedasticity is the spread of the variance of one variable is the same all the way down the other variable. And that sounds clear as mud. So let me kind of show you a picture. This is from the field book. And so if you think about this as x down here, and this is y over here, the spread of the dots has to be the same all the way across. So you don't get this triangle shape where the spread is small on one end and large on the other. That would be bad. That would be a heteroscedastic issue. And so you want the spread to be the same all the way across. So what we're going to do is check a residual scatter plot for these. And so we're going to create a scatter plot of that fake regression. So on our x-axis, what we're going to do is get the fitted values. Fitted values are what we would have predicted y to be all across all the variables. So this is a way to combine all of the variables into one score to plot them all in one graph. And we're predicting a random score, so our fitted values predicting a random score should be random. And we're going to standardize those. We're standardizing them to make the scale z, and that makes things a little easier. So let's do that first. Okay, so to get this graph, so this is Homog and Homog+s, we're going to create our fitted values first. So I'm going to call this fitted. So we use this scale function, that'll z-score it. It's fake $ fitted values, fitted dot values, to pull out those values. So that creates me a list of calculated scores for all of my x variables. The y-axis is going to be the standardized residuals that we've been using this whole time, so the difference between their predicted score, which is the fitted values, and their actual score. So this should be random because we're predicting a random variable. And they're both standardized at this point to make them easier to interpret. So we're plotting them against each other. So these residuals should be randomly distributed because we're predicting a random variable. And so it should look like a bunch of random dots. So that's why random variables and y chi-square. So we did this fit values things already. So I called them fitted just now. And we're going to plot them against each other. So very simple plot function. So fitted values, so it's x comma y. And so standardized. Okay. And that creates us this plot that you don't have any idea how to interpret, but let me show you. Let's add some lines to it. I'm going to do AB line again at 0, 0. So that'll draw me a straight line at 0. And then actually something that's not on the notes, AB line V equals 0 for vertical equals 0. And I guess you could have done AB line H equals 0. Either way. And that creates me this plot. Okay. So I'm going to add that real quick to my notes, because that's something we figured out in class. Alright, so with my plot here, what am I looking for? Well, what you want is the spread. And I'm going to take a real quick picture of this so I can draw on it in Word. There we go. I'm going to delete all of this real quick. So for homogeneity, sorry, I thought that might be a little faster. There we go. I want the spread of the dots to be even on each side of 0. So I want the spread this way to be the same. Oh, why'd you do that little line? Got it too excited. The spread this way to be the same as the spread this way. And so what I tell people to do is sort of draw themselves a line around where most of the dots are. So this to... Sorry, my computer's unhappy with all this drawing. There we go. To where's... Gracious, I can't operate Word. So let's get rid of that one. Make a little line come back here. Here. Okay, and that's where most of the dots are. So it's running from -2 to +2. So that's pretty homogenetic because most of the dots are centered around 0. Okay, it's a little more on the top than the bottom, but be a little forgiving. You'd also want to do that going up and down. So most of the dots are between 2. That's where most of them are. They've got a big gap here. Those are our little random dudes. They always happen. And 2. If I could draw straight lines, there we go. So most of the dots are between 2 and 2 still, and it's mostly centered around 0. So really, that's what the 0 line is for on this graph. You want to make sure there's basically the same number of people in each quadrant. Don't literally count them, but like, does it look like approximately the same number of people in each quadrant? And is that spread pretty even around 0? So you don't want too many to have a bunch below 0 and not as many above 0. that would be raining. So this is like, you don't want it to look like it's a cloud formation hovering around 0 where one side is getting rained on. So that's homogeneity. Homoscedasticity is about the actual shape of the dots. So you can ignore the 0 here. And I think on my slides I have that slightly incorrect, so let me fix that real quick. You want the spread to be around 0, all the way across the x-axis here. Let's do that. Okay, so is the spread equal all the way across x? It should look like a bunch of dots. So I'm going to take this function, this one, and do some very awesome scribble lines. So I'm going to draw around my potato here around the dots, around most of the dots. Ah, wrong one. This squiggle line should give us no, oh my gosh, colored lines here. So I don't know why that suddenly is adding no fill. And make it transparent. I don't know. Okay, some days it'll allow you to do it without the background. Today it's being mean to me. That one? Whatever. So you get the idea. So if it makes a blob of dots or a circle here, you're good. If instead the dots go off and make a triangle, that's bad. So again, be a little forgiving. So drawing an imaginary line, or if you can get Word to work appropriately, drawing a real line around the dots, it shouldn't make a triangle or a UFO or a shark. I had a student that would play connect the dots for me and make me funny pictures. It should just look like a random blob of dots. Okay, and so that's about the dots themselves. It's not about centering over 0. So that's homoscedasticity. Okay, so it should look like a bunch of random dots. So that's how you check for the big assumptions for linear models. And that includes additivity, linearity, normality, homogeneity, and homoscedasticity.